Hi, I'm Nigel, and I'm going to talk today about equations in maths and physics. What's the difference? Well, let's start with an example. Here's an equation. A divided by B equals C. So the first question, well, what's A, B, and C? What are they? I'm not saying. Okay, it's a little bit unfair. What I'm saying here is that A, B, and C and A over B equals C is an equation which represents a relationship between abstract quantities A, B, and C. That means that this is a formal equation. Now, I haven't really said very much. What does it mean to say that they're abstract quantities? It doesn't really mean much, does it? But it does mean that I can rearrange the equation any way I want. A over B equals C, therefore B equals A over C, or A equals BC. Because I haven't defined A, B, and C, that means there's no restriction on me on how I can algebraically manipulate the equation. In other words, less information is equal to greater freedom. Supposing now I say, okay, A, B, and C, they're numbers. Well, first of all, this gives us what I call a restriction alert. Saying that A, B, and C are numbers means that B, as the equation is A over B equals C, the B there, cannot be equal to 0 because you are not allowed to divide by 0 in mathematics. So equations with numbers have restrictions, whereas equations where you don't define the objects or abstract quantities as numbers, there aren't any restrictions. Let's make a further description of what A, B, and C are. I'm now going to say, guess what? A, B, and C, not only are they numbers, but they represent physical properties. Physical properties that we can measure. So for example, A is a distance, in this case, the distance that this stick man, that I'm very poorly drawn stick man, is running away from this brick wall. And the distance he's gone, A, after a time, B, will give us his velocity, or his average velocity, which is A divided by B, and I'm going to call that velocity C. A over B equals C is now a physics equation. It's not a maths equation, it's not an abstract quantity equation or a number equation, it's a physics equation. Restriction alert. Okay, more restrictions. Well, the first thing that I could say is because of the physical circumstances of the man running away from the wall, the A, the distance that he or she is traveling from the wall, cannot be negative. Similarly, the time, B, measured on a stopwatch, I'm going to start at when the person starts running from the wall, so B also cannot be less than 0. So the physical circumstances give rise to physical restrictions. The only way which A can be less than 0 is if the wall doesn't exist or there's a hole in it or something like that. Now, because it's a physics equation, A over B equals C, we've got two more types of restrictions. And the second one, apart from the physics restrictions, the physical restrictions, is the two types are on dimensions and units. Now, this is something that often causes confusion. What is a dimension and what is a unit? The way to think of it is that dimensions simply are what things are. They just simply describe what they are, whereas the units are what they're actually measured in. So A, in my example, is a length, so therefore it has dimensions of length. And I represent the dimensions of length with a capital letter L. And the normal thing is to put L in square brackets. That denotes that I'm talking about the dimensions length. B is the time, and this has the dimensions of time, and therefore I represent it by a capital letter T. C is the velocity. This has the dimensions of velocity, and the dimensions of velocity are length divided by time, which we represent here as Lt to the minus 1. Again, in square brackets. Now, units are what the physical quantities, the dimensions, are actually measured in. Now, we use normally the SI system. Not exclusively, but it's a system that is used in science, where we use kilograms for measuring mass, we use seconds for measuring time, and we use meters for measuring lengths. There are also other units. We use, these units are often named after famous people. There's a little convention here. The names of the symbols, the letters that represent the symbols, and the person who the symbol is named after. So, for example, I can write here Isaac Newton. Newton's unit of force is called the Newton, and we use the symbol N. And here, Isaac Newton has a capital letter because it's a proper noun. The unit of force is called the Newton. This is a common noun, and it therefore has a small letter or lowercase letter. And the symbol for newtons is capital N. So it's the Newton is small n, and the name of the person and the actual letter that we use is capital. So that's the units that we use. We also have other dimensions that other than mass, length, and time. For example, we have temperature, which is measured in degrees Kelvin, and we have current, which is measured in amperes, and there's also luminous intensity, which we measure in candelas, and the amount of substance, the mole, which we measure in moles. So there are other dimensions and there are other units. Now the restriction A over B equals C. So if this is a physical equation, then as I said, we've got physical restrictions which depend on the circumstances, and then there are restrictions on the dimension and the unit. These together are called homogeneity. And the homogeneity dictates that the dimensions and units on both sides of this equals sign have to be the same. So if A over B is length over time, then C has the dimensions length over time. And if A is measured in meters and B is measured in seconds, then C has to be measured in meters per second. And the reason, basically, you can't equate apples and pears. They're different things, and therefore we cannot have different dimensions and different units on each side of an equal sign of a physics equation. What this actually means is that there's a hierarchy of equations. So A over B equals C. If we don't define A, B, and C, then this is a maths equation, and it's an abstract equation called a formal equation. No restrictions, We can manipulate the A over B equals C any way algebraically we like. We don't have to worry about that. We have complete freedom, but we don't have much information. If I then say that this is a maths equation, but A, B, and C are numbers, then that gives us more information, but it gives us more restrictions. For instance, A over B equals C, B can't be 0, or if I put this equation in the form A over C equals B, then the C can't be equal to 0. It depends on how the equation actually looks and what's on the denominator. And the rule, funnily enough, is while it's an abstract equation, you can manipulate it as much as you like. It's only when it becomes a number equation you have these restrictions. And you can, as it were, hold off deciding what A, B, and C are when you write down the equation and keep it formal, keep it as an abstract equation, do your manipulations, and then when you then decide to make it a number equation, the equation you've got left, as it were, after your manipulations, that's the equation where you apply the restrictions. And then finally, if you say, well, really, this is a physics equation, then you bring in even more restrictions, but you do have more information. So that's the pattern between maths equations and physics equations. I'll leave you with our advert on books we produce, and you can look on this website to order books if you want. Bye.